Hello and welcome. Today we'll be looking at elongation of a conical bar due to its self weight. First, diagram above the diagram of a conical bar. Having a, a top diameter to be D and the length is L and the self weight is W. Now, for us to calculate the elongation, first thing we are going to do we are going to consider a differential element because as we move from the top from the bottom to the top we observe that there's a variation in the area, so the area is not uniform. That is why we are going to consider more section, that is differential element, which is C, E, D and what. That is what we are going to do. All right, so by the time we get the deformation of this differential element and therefore integrate it from the bottom to the top, then we get the elevation of back. So let's get started. So we have two triangles here, triangle A, B and G, and triangle E, F and G. Similar triangle and say AB all over what? EF is equal to the length of what? Length L all over what? 1. We can therefore say AB all over EF equals to what? Equals to L all over what? And we know that our AB is what? D. We have D all over what? All over DS, which will be equals to what? Which will be equals to L all over what? Y. By the time we make the X the subject, we are going to have X equals to YD all over what? X. So let's put the. All right. So from here, the next thing we are going to consider is self weight. Self weight W, please let me put self weight here. W will be equals to weight density, is omega times volume. Note that the volume we are considering here is the volume of the differential element because we want to consider the differential element now. All right. So, and we know that our weight density here, omega, is nothing but density times what? Gravity times the volume of the differential element. Also be taken as the volume of a what? Of a cone. And we know that the volume of a cone is what? By r square L all over what? 3. But the length of the differential element from this point to this point is the length y. So our L will be taken as y. And the radius here, we know the diameter of this differential element is nothing but what? The S. So we are going to see our weight equals to b times b times pi into, you know, radius is d all over what? 2. But we are going to write the diameter in form of what? S. All over 2 all square multiplied by y all over what? All over 3. All right, so from here, I'm going to take our self weight equals to density T times pi times, we're going to have the S squared all over 4 times y all over 1, all over 3. So from here, I'm going to have our W. I'm going to have our W, this G, then pi. Then we are going to have, so we are going to have our y all over 1, all over 3. Because it's 4 will come down 4 times 3. But don't forget, our S is equal to what? YD over L. So we substitute that here. Weight density further be multiplied as this G pi then into what? Into YD all over L Y squared all over what? All over 2. By the time we open that bracket, we're going to have our weight density this pi into y square b square all over L square, then y all over 1. So finally, we can write our weight density as density, gravity, pi, and the y cube b square all over 1. Where this is our weight, our weight, self weight of this conical bar. That is it. So the next thing we are going to analyze. Right. Sorry, this is supposed to be L square. All right. So from here, and therefore analyze for the stress. So let's analyze for the stress in the differential element. So we know that our stress is equals to this load all over what? Area. All right. And our load, so we can say stress is equal to what is load? Load is density, gravity by y cube, then d square all over 12L square, 12L square all over area. Our area is by d square, but d will be writing in form of what? S, because we are considering the stress in the differential element. D square all over what? 4. All right, so by the time we do this, we are going to have our stress equals to d by y cube d square all over what? 12L square multiplied by 4 all over what? By what? By the S. All right. So by the time we do this, we are going to have pi, go with pi, 4 year 1, 4 year 15. So we can therefore write our stress as density, gravity, y cube, d square, all over 1, all over 3L square, 3L square, S square. All right, but don't forget, we already said our dx is nothing but what? Yd all over x from this part. So our dx, I'm going to substitute for the s here. So let me clean this part. We're going to have our stress equals to density, gravity, y cube, d square, all over what? All over 3L square. The s is nothing but what? L is nothing but yd all over s all square. All right. So from here, if I open this bracket again, I'm going to have stress equals to 5 cube all over 1. If I open this, I'm going to have 3L square into multiply by, that is y square d square all over 1 L square. All right. So now you see that L square will go with L square, d square will go with d square, this y square will go with what? 2 of the 3y that is here. Now we'll be left with stress equals to density, gravity, y all over 1, all over 3. So this is the stress in differential elements. All right. So the next thing is we're also going to recall from our Hooke's law. Know that our Young modulus, Young modulus. So Young modulus is denoted by E equals to stress all over what? All over strain, right? Uh, from our modulus of elasticity, rather, equals to stress all over what? Strain. Because it's also known as the word Young modulus. All right, so now from here, we can substitute our stress here. Once we get our stress, put it there, then, okay, let's do that then. This will be equals to this dy all over what? All over 3, all over 3. To be understanding. Everything here over E, 3 will go down to now, but don't forget that our strain can also be written as our strain. Our strain E can be written as L all over what? L. But we are considering differential element, right? So that is our L here will become our Y, and our DL is going to be our DY. So if we do that, all right, sorry. We said strain is equal to the L all over what? Y. That is the deformation all over what? The original length. This the original length. And the original length of this differential element is what? The Y. So now our strain equals to the L all over what? Y. So if I substitute this in this place, I'm going to have my modulus of elasticity equals to density, gravity, y, all over what? All over 3 into the L, all over the y. But mind you, I like writing my y. Let's take it like this. So now from here, by cross multiply, sorry, no, okay, let's open the bracket first. I'm going to have, let me say, all over 3 L, all over 1. By the time you do this y will go back up. So we are going to have e to be equals to y all over what? 3L, then multiply by. Alright, so if I make the L the subject, that is the elongation, here I'm going to have elongation here equals to density, gravity, y all over what? 3E. So this elongation that you are seeing here is the elongation of the what? Differential element. So now that we have gotten the elongation of the differential element, we can therefore integrate from the bottom to the top. So when we integrate this, we are going to get the total we are going to get the total elongation of this conical bar. And guess what? So now, from here, we are going to integrate, we are integrating from 0 to what? To L. Because the total length is what? L. By the time we integrate that, get the total elongation. Alright, so from here, I'm going to have L to be equals to integration from 0 to L of density, gravity, y, all over what? All over 3E y. Alright, so we are integrating in respect to y. So it means density, gravity, all over 3L will be a constant, will come back. So we are going to have the L to be equals to gravity all over 3E, integration from 0 to L of y to y. By the time we integrate that, we're going to get this density, gravity all over 3E into y squared all over what? 2, then from 0 to what? To L. Alright, so by the time we do that, we're going to get L to be equals to this over 3E into, put the upper and the lower limit to be left with L squared all over 1, all over. We have to put 0 divided by 2, 0 minus 8. Alright, so I'm going to have our total deformation equals to density, gravity, all over what? All over C. So this is the total, sorry, L. This is the total deformation in this conical bar. But we can further modify this. So here we love showing you everything So let's further modify this. So let's further modify. So we know that here we can write this formula as L equals to, we know weight density is nothing but what? Density times gravity, which we denote it as what? Omega. So we can write this as omega L square all over what? All over 6. All right, so let's further modify this again. We know that the self weight W is equals to what? Is equals to weight density, which is denoted by omega, times volume, right? All right. Let's make our weight density. Sorry, yeah. Let's make the weight density here the subject. So we are going to have omega to be equals to this the weight of the cone. This is the self weight all over what? All over volume. All right. So by so doing, we can therefore write, we know that the weight is W. So we know that our self weight is W, which is here. Now, we want to write the volume now. No, we want to consider the whole cone. So we want to write the volume now in form of what? In form of the area of the base of this cone. But we know that the volume is nothing but what? Volume is nothing but, I write this as W all over what? Volume is what? Is pi, then R square L all over what? 3, right? But here we can write our R to be W, the omega will be equal to W all over what? All over pi. Then we are going to have P all over what? All over 2, all square. Then we have L, everything over 3. By the time we open this, we're going to have this to be equal to this the weight of the cone all over what? All over pi. We have b square, we have L, then we have 2 to power 4, 2 is 4, 4 times 3 is 12. So from here, that is what we are going to get. All right, so from here, if I decide, I can write this 12 in form of 3 times 4. So if I write this in form of 3 multiplied by 4. And if you know the area of our base, area of our base denoted by AB is nothing but what? Nothing but pi d square all over what? All over 4. So pi d square all over 4 is already here. So let's split it so we can bring out pi d square all over 4. Omega, which is our weight density, is equals to this the weight of the cone all over. Now let's bring out pi d square all over 4. If I bring out pi d square all over 4, I'll be left with L over 3. L over 3. Right? Now we know that pi d square all over 4 is equal to the base area of the cone. So we can replace everything here with the area of the base. So our omega will be equals to U all over what? AB L all over 3, which will be equals to 3W all over what? ABL. All right. So now we substitute this now into this formula now. So let's substitute this into this formula. We are going to have our L elongation to be equals to omega, but our omega is what? This weight density is equals to 3W all over what? AEL multiplied by L squared all over what? All over 6E. All over 6. And you know that this L here will go with one of these L. Then we can and we can write this as this go up. Then we will write this as 3 omega. Sorry, this is not omega. This is W. Okay. W. 3W Then we are going to have this is going to come up here. We are going to have 3 WL all over AB 60. So this 3 will go here, 3 here 1, 3 here. So we can further rewrite this as L to be equals to weight of the pole all over the that is weight of the pole times length all over base area. We have 3 that is 2. This is another form of writing equation of the elongation of the conical bar. This is don't forget to give this video a thumbs up and don't forget to share with your friends.